The Integral Fast Reactor, IFR, originally Advanced Liquid Metal Reactor, is a design for a nuclear reactor using fast neutrons and no neutron moderator. A fast reactor, IFR, is distinguished by a nuclear fuel cycle that uses reprocessing via electrorefining at the reactor site. IFR development began in 1984 and the U.S. Department of Energy built a prototype, the Experimental Breeder Reactor II. On April 3, 1986, two tests demonstrated the inherent safety of the IFR concept. These tests simulated accidents involving loss of coolant flow, even with its normal shutdown devices disabled. The reactor shut itself down safely without overheating anywhere in the system. The IFR project was cancelled by the U.S. Congress in 1994. 3 years before completion, the proposed generation IV sodium-cooled fast reactor is its closest surviving fast breeder reactor design. Other countries have also designed and operated fast reactors. S-PRISM, from SuperPRISM, also called PRISM, Power Reactor Innovative Small Module, is the name of a nuclear power plant designed by GE Hitachi Nuclear Energy, GE, based on the Integral Fast Reactor. Overview. The IFR is cooled by liquid sodium lead and fueled by an alloy of uranium and plutonium. The fuel is contained in steel cladding with liquid sodium filling in the space between the fuel and the cladding. A void above the fuel allows helium and radioactive xenon to be collected safely without significantly increasing pressure inside the fuel element, and also allows the fuel to expand without breaching the cladding, making metal rather than oxide fuel practical. The advantage of lead as opposed to sodium is that it is not reactive chemically, especially with water or air. The disadvantages are that liquid lead is far more viscous than liquid sodium, increasing pumping costs, and there are numerous radioactive neutron activation products, while there are essentially none from sodium. Basic design decisions equals metallic fuel equals metal fuel with a sodium-filled void inside the cladding to allow fuel expansion has been demonstrated in EBR2. Metallic fuel makes pyroprocessing the reprocessing technology of choice. Fabrication of metallic fuel is easier and cheaper than ceramic oxide fuel, especially under remote handling conditions. Metallic fuel has better heat conductivity and lower heat capacity than oxide, which has safety advantages. Sodium coolant equals use of liquid metal coolant removes the need for a pressure vessel around the reactor. Sodium has excellent nuclear characteristics, a high heat capacity and heat transfer capacity, low viscosity, a reasonably low melting point in a high boiling point, and excellent compatibility with other materials including structural materials and fuel. The high heat capacity of the coolant and the elimination of water from the core increase the inherent safety of the core. Pool design rather than loop containing all of the primary coolant in a pool produces several safety and reliability advantages. On-site reprocessing using pyroprocessing reprocessing is essential to achieve most of the benefits of a fast reactor, improving fuel usage and reducing radioactive waste each by several orders of magnitude. On-site processing is what makes the IFR integral. This and the use of pyroprocessing both reduce proliferation risk. Pyroprocessing, using an electrorefiner, has been demonstrated at EBR2 as practical on the scale required, compared to the PUREX aqueous process. It is economical in capital cost, and is unsuitable for production of weapons material. Again, unlike PUREX, which was developed for weapons programs, pyroprocessing makes metallic fuel the fuel of choice. The two decisions are complementary. Summary The four basic decisions of metallic fuel, sodium coolant, pool design, and on-site reprocessing by electrorefining, are complementary, and produce a fuel cycle that is proliferation-resistant and efficient in fuel usage, and a reactor with a high level of inherent safety, while minimizing the production of high-level waste. The practicality of these decisions has been demonstrated over many years of operation of EBR2. Advantages: breeder reactors, such as the IFR, could in principle extract almost all of the energy contained in uranium or thorium, decreasing fuel requirements by nearly 2 orders of magnitude compared to traditional once-through reactors, which extract less than 0.65% of the energy in mined uranium, and less than 5% of the enriched uranium with which they are fueled. This could greatly dampen concern about fuel supply or energy used in mining. In fact, seawater uranium extraction could provide enough fuel for breeder reactors to satisfy our energy needs indefinitely, thus making nuclear energy as sustainable as solar or wind renewable energy. Fast reactors can burn long-lasting nuclear transuranic waste (TRU) waste components, actinides, reactor-grade plutonium and minor actinides, turning liabilities into assets. Another major waste component, fission products, would stabilize at a lower level of radioactivity than the original natural uranium ore it was attained from in 2 to 4 centuries, rather than tens of thousands of years. The fact that fourth-generation reactors are being designed to use the waste from third-generation plants could change the nuclear story fundamentally, potentially making the combination of third- and fourth-generation plants a more attractive energy option than third-generation by itself would have been, both from the perspective of waste management and energy security. The use of a medium-scale reprocessing facility on site, and the use of pyroprocessing rather than aqueous reprocessing, is claimed to considerably reduce the proliferation potential of possible diversion of fissile material as the processing facility is in situ. Integral safety. In traditional light water reactors, LWRs, the core must be maintained at a high pressure to keep the water liquid at high temperatures. In contrast, since the IFR is a liquid metal-cooled reactor, the core could operate at close to ambient pressure, dramatically reducing the danger of a loss of coolant accident. The entire reactor core, heat exchangers and primary cooling pumps are immersed in a pool of liquid sodium and lead, making a loss of primary coolant extremely unlikely. The coolant loops are designed to allow for cooling through natural convection, meaning that in the case of a power loss or unexpected reactor shutdown, the heat from the reactor core would be sufficient to keep the coolant circulating even if the primary cooling pumps were to fail. The IFR also has passive safety advantages as compared with conventional LWRs. The fuel and cladding are designed such that when they expand due to increased temperatures, more neutrons would be able to escape the core, thus reducing the rate of the fission chain reaction. In other words, an increase in the core temperature will act as a feedback mechanism that decreases the core power. This attribute is known as a negative temperature coefficient of reactivity. Most LWRs also have negative reactivity coefficients. However, in an IFR, this effect is strong enough to stop the reactor from reaching core damage without external action from operators or safety systems. This was demonstrated in a series of safety tests on the prototype. Pete Planken, the engineer who conducted the tests for an international audience, quipped, "Back in 1986, we actually gave a small 20 MWe prototype advanced fast reactor a couple of chances to melt down. It politely refused both times." Quote, Liquid sodium presents safety problems because it ignites spontaneously on contact with air and can cause explosions on contact with water. This was the case at the Monju nuclear power plant in a 1995 accident and fire. To reduce the risk of explosions following a leak of water from the steam turbines, the IFR design, as with other sodium-cooled fast reactors, includes an intermediate liquid metal coolant loop between the reactor and the steam turbines. The purpose of this loop is to ensure that any explosion following accidental mixing of sodium and turbine water would be limited to the secondary heat exchanger and not pose a risk to the reactor itself. Alternative designs use lead instead of sodium as the primary coolant. The disadvantages of lead are its higher density and viscosity, which increases pumping costs, and radioactive activation products resulting from neutron absorption. A lead bismuth eutectate, as used in some Russian submarine reactors, has lower viscosity and density, but the same activation product problems can occur. Efficiency and fuel cycle. The goals of the IFR project were to increase the efficiency of uranium usage by breeding plutonium, and eliminating the need for transuranic isotopes ever to leave the site. The reactor was an unmoderated design running on fast neutrons, designed to allow any transuranic isotope to be consumed, and in some cases used as fuel, compared to current light water reactors with a once-through fuel cycle that induces fission, and derives energy from less than 1% of the uranium found in nature. A breeder reactor like the IFR has a very efficient 99.5% of uranium undergoes fission. Fuel cycle. The basic scheme used pyroelectric separation, a common method in other metallurgical processes, to remove transuranics and actinides from the wastes and concentrate them. These concentrated fuels were then reformed on site into new fuel elements. The available fuel metals were never separated from the plutonium isotopes nor from all the fission products, and therefore relatively difficult to use in nuclear weapons. Also, plutonium never had to leave the site, and thus was far less open to unauthorized diversion. Another important benefit of removing the long half-life transuranics from the waste cycle is that the remaining waste becomes a much shorter-term hazard. After the actinides, reprocessed uranium, plutonium, and minor actinides are recycled, the remaining radioactive waste isotopes are fission products, with half-life of 90 years, EDM 151, or less at 211,100 years, TC 99, and more, plus any activation products from the non-fuel reactor components. Comparisons to light water reactors. Nuclear waste. IFR-style reactors produce much less waste than LWR-style reactors, and can even utilize other waste as fuel. The primary argument for pursuing IFR-style technology today is that it provides the best solution to the existing nuclear waste problem because fast reactors can be fueled from the waste products of existing reactors as well as from the plutonium used in weapons, as is the case in the operating, as of 2014, BN800 reactor. Depleted uranium (DU) waste can also be used as fuel in fast reactors. The waste products of IFR reactors either have a short half-life, which means that they decay quickly and become relatively safe, or a long half-life, which means that they are only slightly radioactive. Due to pyroprocessing, the total volume of true waste fission products is 1/20th the volume of spent fuel produced by a light water plant of the same power output, and is often all considered to be waste. 70% of fission products are either stable or have half-lives under 1 year. Technetium-99 and iodine-129, which constitute 6% of fission products, have very long half-lives but can be transmuted to isotopes with very short half-lives, 15.46 seconds and 12.36 hours, by neutron absorption within a reactor, effectively destroying them. See more long-lived fission products. Zirconium-93. Another 5% of fission products could in principle be recycled into fuel pin cladding, where it does not matter that it is radioactive, excluding the contribution from transuranic waste, TRU, which are isotopes produced when U-238 captures a slow thermal neutron in a LWR but does not fission. All the remaining high-level waste fission products left over from reprocessing out the TRU fuel is less radiotoxic in sieverts than natural uranium, in a gram-to-gram comparison, within 400 years, and it continues its decline following this. Edwin Sayre has estimated that a ton of fission products, which also include the very weakly radioactive palladium-107 etc., reduced to metal, has a market value of $16 million. The two forms of IFR waste produced contain no plutonium or other actinides. The radioactivity of the waste decays to levels similar to the original ore in about 300 to 400 years. The on-site reprocessing of fuel means that the volume of high-level nuclear waste leaving the plant is tiny compared to LWR spent fuel. In fact, in the U.S., most spent LWR fuel has remained in storage at the reactor site instead of being transported for reprocessing or placement in a geological repository. The smaller volumes of high-level waste from reprocessing could stay at reactor sites for some time, but are intensely radioactive from medium-lived fission products, MLFPs, and need to be stored securely, like in the present dry cask storage vessels. In its first few decades of use, before the MLFPs decay to lower heat-producing levels, geological repository capacity is constrained not by volume but by heat generation, and decay heat generation from medium-lived fission products is about the same per unit power from any kind of fission reactor, limiting early repository emplacement. The potential complete removal of plutonium from the waste stream of the reactor reduces the concern that presently exists with spent nuclear fuel from most other reactors that arises with burying or storing their spent fuel in a geological repository, as they could possibly be used as a plutonium mine at some future date. Despite the million-fold reduction in radiotoxicity offered by this scheme, some believe that actinide removal would offer few if any significant advantages for disposal in a geologic repository because some of the fission product nuclides of greatest concern in scenarios such as groundwater leaching actually have longer half-lives than the radioactive actinides. These concerns do not consider the plan to store such materials in insoluble synrock, and do not measure hazards in proportion to those from natural sources such as medical X-rays, cosmic rays, or natural radioactive rocks, such as granite. These persons are concerned with radioactive fission products such as technetium-99, iodine-129, and cesium-135 with half-lives between 213,000 and 15.7 million years, some of which are being targeted for transmutation to belay even these comparatively low concerns. For example, the IFR's positive void coefficient could be reduced to an acceptable level by adding technetium to the core, helping destroy the long-lived fission product technetium-99 by nuclear transmutation in the process. See more long-lived fission products. Efficiency. IFRs use virtually all of the energy content in the uranium fuel, whereas a traditional light water reactor uses less than 0.65% of the energy in mined uranium, and less than 5% of the energy in enriched uranium. Carbon dioxide. Both IFRs and LWRs do not emit CO2 during operation, although construction and fuel processing result in CO2 emissions. If energy sources which are not carbon neutral, such as fossil fuels, or CO2-emitting cements are used during the construction process. A 2012 Yale University review published in the Journal of Industrial Ecology analyzing CO2 life cycle assessment emissions from nuclear power determined that the collective LCA literature indicates that life cycle GHG greenhouse gas emissions from nuclear power are only a fraction of traditional fossil sources and comparable to renewable technologies. Quote, although the paper primarily dealt with data from Generation II reactors, and did not analyze the CO2 emissions by 2050 of the presently under construction Generation III reactors, it did summarize the life cycle assessment findings of in-development reactor technologies. Theoretical FBRs, fast breeder reactors, have been evaluated in the LCA literature. The limited literature that evaluates this potential future technology reports median life cycle GHG emissions, similar to or lower than LWRs, light water reactors, and purports to consume little or no uranium or fuel cycle. Fast reactor fuel must be at least 20% fissile, greater than the low enriched uranium used in LWRs. The fissile material can initially include highly enriched uranium or plutonium from LWR spent fuel, decommissioned nuclear weapons, or other sources. During operation, the reactor breeds more fissile material from fertile material, at most about 5% more from uranium, and 1% more from thorium. The fertile material in fast reactor fuel can be depleted uranium, mostly U-238, natural uranium, thorium, or reprocessed uranium from spent fuel from traditional light water reactors, and even include non-fissile isotopes of plutonium and minor actinide isotopes, assuming no leakage of actinides to the waste stream during reprocessing. A 1 GWE IFR-style reactor would consume about 1 ton of fertile material per year and produce about 1 ton of fission products. The IFR fuel cycles reprocessing by pyroprocessing. In this case, electrorefining does not need to produce pure plutonium free of fission product radioactivity as the PUREX process is designed to do. The purpose of reprocessing in the IFR fuel cycle is simply to reduce the level of those fission products that are neutron poisons. Even those need not be completely removed. The electro-refined spent fuel is highly radioactive, but because new fuel need not be precisely fabricated like LWR fuel pellets but can simply be cast, remote fabrication can be used, reducing exposure to workers. Like any fast reactor, by changing the material used in the blankets, the IFR can be operated over a spectrum from breeder to self-sufficient to burner. In breeder mode, using U-238 blankets, it will produce more fissile material than it consumes. This is useful for providing fissile material for starting up other plants, using steel reflectors instead of U-238 blankets. The reactor operates in pure burner mode and is not a net creator of fissile material. On balance, it will consume fissile and fertile material and, assuming loss-free reprocessing, output no actinides but only fission products and activation products. Amount of fissile material needed could be a limiting factor to very widespread deployment of fast reactors. If stocks of surplus weapons plutonium and LWR spent fuel plutonium are not sufficient to maximize the rate at which fast reactors can be deployed, they can be operated in maximum breeding mode. Because the current cost of enriched uranium is low compared to the expected cost of large-scale pyroprocessing and electrorefining equipment, and the cost of building a secondary coolant loop. The higher fuel costs of a thermal reactor over the expected operating lifetime of the plant are offset by increased capital cost. Currently in the United States, utilities pay a flat rate of 1/10 cent per kilowatt-hour to the government for disposal of high-level radioactive waste by law under the Nuclear Waste Policy Act. If this charge were based on the longevity of the waste, closed fuel cycles might become more financially competitive. As the planned geological repository in the form of Yucca Mountain is not going ahead, this fund has collected over the years, and presently $25 billion has piled up on the government's doorstep for something they have not delivered. That is, reducing the hazard posed by the waste. Reprocessing nuclear fuel using pyroprocessing and electrorefining has not yet been demonstrated on a commercial scale, so investing in a large IFR-style plant may be a higher financial risk than a conventional light water reactor. Passive safety. The IFR uses metal alloy fuel, uranium, plutonium, zirconium, which is a good conductor of heat. Unlike the LWRs, and even some fast breeder reactors, uranium oxide, which is a poor conductor of heat and reaches high temperatures at the center of fuel pellets. The IFR also has a smaller volume of fuel, since the fissile material is diluted with fertile material by a ratio of 5 or less, compared to about 30 for LWR fuel. The IFR core requires more heat removal per core volume during operation than the LWR core. But on the other hand, after a shutdown, there is far less trapped heat that is still diffusing out and needs to be removed. However, decay heat generation from short-lived fission products and actinides is comparable in both cases, starting at a high level and decreasing with time elapsed after shutdown. The high volume of liquid sodium primary coolant in the pool configuration is designed to absorb decay heat without reaching fuel melting temperature. The primary sodium pumps are designed with flywheels so they will coast down slowly, 90 seconds. If power is removed, this coast down further aids core cooling upon shutdown. If the primary cooling loop were to be somehow suddenly stopped, or if the control rods were suddenly removed, the metal fuel can melt as accidentally demonstrated in EBRI. However, the melting fuel is then extruded up the steel fuel cladding tubes and out of the active core region, leading to permanent reactor shutdown and no further fission heat generation or fuel melting. With metal fuel, the cladding is not breached and no radioactivity is released even in extreme overpower transients. Self-regulation of the IFR's power level depends mainly on thermal expansion of the fuel, which allows more neutrons to escape, damping the chain reaction. LWRs have less effect from thermal expansion of fuel, since much of the core is the neutron moderator, but have strong negative feedback from Doppler broadening, which acts on thermal and epithermal neutrons, not fast neutrons, and negative void coefficient from boiling of the water moderator, coolant. The less dense steam returns fewer and less thermalized neutrons to the fuel, which are more likely to be captured by U-238 than induce fissions. However, the IIFR's positive void coefficient could be reduced to an acceptable level by adding technetium to the core, helping destroy the long-lived fission product technetium-99 by nuclear transmutation in the process. IFRs are able to withstand both a loss of flow without scram and loss of heat sink without scram. In addition to passive shutdown of the reactor, the convection current generated in the primary coolant system will prevent fuel damage, core meltdown. These capabilities were demonstrated in the EBR-II. The ultimate goal is that no radioactivity will be released under any circumstance. The flammability of sodium is a risk to operators. Sodium burns easily in air, and will ignite spontaneously on contact with water. The use of an intermediate coolant loop between the reactor and the turbines minimizes the risk of a sodium fire in the reactor core. Under neutron bombardment, sodium-24 is produced. This is highly radioactive, emitting an energetic gamma ray of 2.7 MeV followed by a beta decay to form magnesium-24. Half-life is only 15 hours, so this isotope is not a long-term hazard. Nevertheless, the presence of sodium-24 further necessitates the use of the intermediate coolant loop between the reactor and the turbines. Proliferation. IFRs and light water reactors, LWRs, both produce reactor-grade plutonium, and even at high burn-ups remains weapons usable. But the IFR fuel cycle has some design features that would make proliferation more difficult than the current PUREX recycling of spent LWR fuel. For one thing, it may operate at higher burn-ups and therefore increase the relative abundance of the non-fissile, but fertile, isotopes plutonium-238, plutonium-240 and plutonium-242. Unlike PUREX reprocessing, the IIFR's electrolytic reprocessing of spent fuel did not separate out pure plutonium, and left it mixed with minor actinides and some rare earth fission products, which make the theoretical ability to make a bomb directly out of it considerably dubious. Rather than being transported from a large centralized reprocessing plant to reactors at other locations, as is common now in France, from Le Hague to its dispersed nuclear fleet of LWRs, the IIFR pyroprocessed fuel would be much more resistant to unauthorized diversion. The material with the mix of plutonium isotopes in and IFR would stay at the reactor site and then be burnt up practically in situ. Alternatively, if operated as a breeder reactor, some of the pyroprocessed fuel could be consumed by the same or other reactors located elsewhere. However, as is the case with conventional aqueous reprocessing, it would remain possible to chemically extract all the plutonium isotopes from the pyroprocessed, recycled fuel and would be much easier to dissociate from the recycled product than from the original spent fuel, although compared to other conventional recycled nuclear fuel, MOX, it would be more difficult, as the IFR recycled fuel contains more fission products than MOX and due to its higher burn-up, more proliferation-resistant Pu-240 than MOX. An advantage of the IFR's actinides removal and burn-up, actinides include plutonium, from its spent fuel, is to eliminate concerns about leaving the IFR's spent fuel or indeed conventional, and therefore comparatively lower burn-up, spent fuel, which can contain weapons-usable plutonium isotope concentrations in a geological repository, or the more common dry cask storage, which then might be mined sometime in the future for the purpose of making weapons. Quote, because reactor-grade plutonium contains isotopes of plutonium with high spontaneous fission rates, and the ratios of these troublesome isotopes from a weapons manufacturing point of view only increases as the fuel is burnt up for longer and longer. It is considerably more difficult to produce fission nuclear weapons which will achieve a substantial yield from higher burn-up spent fuel than from conventional, moderately burnt-up, LWR spent fuel. Therefore, proliferation risks are considerably reduced with the IFR system by many metrics, but not entirely eliminated. The plutonium from ALMR recycled fuel would have an isotopic composition similar to that obtained from other high burned-up spent nuclear fuel sources, although this makes the material less attractive for weapons production. It could be used in weapons at varying degrees of sophistication, with fusion boosting. The U.S. government detonated a nuclear device in 1962 using then-defined reactor-grade plutonium, although in more recent categorizations it would instead be considered as fuel-grade plutonium, typical of that produced by low-burn-up Magnox reactors. Plutonium produced in the fuel of a breeder reactor generally has a higher fraction of the isotope, plutonium-240, than that produced in other reactors, making it less attractive for weapons use, particularly in first-generation nuclear weapon designs similar to Fat Man. This offers an intrinsic degree of proliferation resistance, but the plutonium made in the blanket of uranium surrounding the core, if such a blanket is used, is usually of a high Pu-239 quality, containing very little Pu-240, making it highly attractive for weapons use. Although some recent proposals for the future of the ALMR-IFR concept have focused more on its ability to transform and irreversibly use up plutonium, such as the conceptual PRISM reactor, and the in-operation 2014 BN-800 reactor in Russia. The developers of the IFR acknowledge that it is uncontested that the IFR can be configured as a net producer of plutonium. Quote, as mentioned above, if operated not as a burner, but as a breeder, the IFR has a clear proliferation potential. If instead of processing spent fuel, the ALMR system were used to reprocess irradiated fertile breeding material, that is, if a blanket of breeding U-238 was used, the resulting plutonium would be a superior material, with a nearly ideal isotope composition for nuclear weapons manufacture. Quote, reactor design and construction. A commercial version of the IFR-S-PRISM can be built in a factory and transported to the site. This small modular design, 311 MWE modules, reduces costs and allows nuclear plants of various sizes, 311 MWE and any integer multiple, to be economically constructed. Cost assessments taking account of the complete life cycle show that fast reactors could be no more expensive than the most widely used reactors in the world, water-moderated water-cooled reactors. Liquid metal NA coolant. Unlike reactors that use relatively slow low-energy thermal neutrons, fast neutron reactors need nuclear reactor coolant that does not moderate or block neutrons, like water does in an LWR, so that they have sufficient energy to fission actinide isotopes that are fissionable but not fissile. The core must also be compact and contain as small amount of material that might act as neutron moderators as possible. Metal sodium Na coolant in many ways has the most attractive combination of properties for this purpose. In addition to not being a neutron moderator, desirable physical characteristics include low melting temperature, low vapor pressure, high boiling temperature, excellent thermal conductivity, low viscosity, lightweight, thermal and radiation stability. Other benefits: abundant in low-cost material. Cleaning with chlorine produces non-toxic table salt, compatible with other materials used in the core. Does not react to dissolve stainless steel, so no special corrosion protection measures needed. Low pumping power, from lightweight and low viscosity, maintains an oxygen and water-free environment by reacting with trace amounts to make sodium oxide or sodium hydroxide and hydrogen, thereby protecting other components from corrosion. Lightweight, low density, improves resistance to seismic inertia events, earthquakes. Drawbacks: extreme fire hazard with any significant amounts of air, oxygen, and spontaneous combustion with water, rendering sodium leaks and flooding dangerous. This was the case at the Monju nuclear power plant in a 1995 accident and fire. Reactions with water produce hydrogen, which can be explosive. Sodium activation product. Isotope. 24Na releases dangerous energetic photons when it decays. However, it has a very short half-life of 15 hours. Reactor design keeps 24Na in the reactor pool and carries away heat for power production using a secondary sodium loop, adding costs to construction and maintenance. Study released by UChicago Argonne. History. Research on the reactor began in 1984 at Argonne National Laboratory in Argonne, Illinois. Argonne is a part of the U.S. Department of Energy's National Laboratory System, and is operated on a contract by the University of Chicago. Argonne previously had a branch campus named Argonne West in Idaho Falls, Idaho, that is now part of the Idaho National Laboratory. In the past, at the branch campus, physicists from Argonne had built what was known as the Experimental Breeder Reactor II, EBR-II. In the meantime, physicists at Argonne had designed the IFR concept, and it was decided that the EBR-II would be converted to an IFR. Charles Till, a Canadian physicist from Argonne, was the head of the IFR project, and Yun Chang was the deputy head. Till was positioned in Idaho, while Chang was in Illinois. With the election of President Bill Clinton in 1992, and the appointment of Hazel O'Leary as the Secretary of Energy, there was pressure from the top to cancel the IFR. Sen. John Kerry, DMA, and O'Leary led the opposition to the reactor, arguing that it would be a threat to non-proliferation efforts, and that it was a continuation of the Clinch River Breeder Reactor project that had been cancelled by Congress. Simultaneously, in 1994, Energy Secretary O'Leary awarded the lead IFR scientist with $10,000 and a gold medal, with the citation stating his work to develop IFR technology provided improved safety, more efficient use of fuel and less radioactive waste. Quote, IFR opponents also presented a report by the DOE's Office of Nuclear Safety regarding a former Argonne employee's allegations that Argonne had retaliated against him for raising concerns about safety, as well as about the quality of research done on the IFR program. The report received international attention, with a notable difference in the coverage it received from major scientific publications. The British journal Nature entitled its article, "Report Backs Whistleblower," and also noted conflicts of interest on the part of a DOE panel that assessed IFR research. In contrast, the article that appeared in Science was entitled, "Was Argonne Whistleblower Really Blowing Smoke?" Quote, remarkably, that article did not disclose that the director of Argonne National Laboratories, Alan Schresheim, was a member of the board of directors of Science's parent organization, the American Association for the Advancement of Science. Despite support for the reactor by then Wahida, Richard Durbin, D. and U.S. Senators Carol Moseley Brown, D. and Paul Simon, D. funding for the reactor was slashed, and it was ultimately cancelled in 1994 by S.A.M.D.T. 2127 to H.R. 4506, at greater cost than finishing it. When this was brought to President Clinton's attention, he said, "I know. It's a symbol." By this time, Senator Kerry and the majority of Democrats had switched to supporting the continuation of the program. The final count was to 52 to 46 to terminate the program, with 36 Republicans and 16 Democrats voting for its termination, while just 8 Republicans and 38 Democrats voted for its continuation. In 2001, as part of the Generation IV roadmap, the DOE tasked a 242-person team of scientists from DOE, UC Berkeley, MIT, Stanford, ANL, LLNL, Toshiba, Westinghouse, Duke, EPRI, and other institutions to evaluate 19 of the best reactor designs on 27 different criteria. The IIFR ranked number 1 in their study, which was released April 9, 2002. At present there are no integral fast reactors in commercial operation. However, a very similar fast reactor, operated as a burner of plutonium stockpiles, the BN800 reactor, became commercially operational in 2014. See also: gas-cooled fast reactor, generation IV reactor, lead-cooled fast reactor, molten salt reactor, traveling wave reactor. References. Further reading. Tom Blees, 2008. Prescription for the Planet. The Painless Remedy for Our Energy and Environmental Crises. Book Surge Publishing. ISBN 1-4196-55825. U.S. Congress. Office of Technology Assessment. May 1994. Technical Options for the Advanced Liquid Metal Reactor. PDF. U.S. Government Printing Office. ISBN 1-4289-2068-4. Charles E. Till. Yunil Chang. 2011. Plentiful Energy. The Story of the Integral Fast Reactor. The Complex History of a Simple Reactor Technology, with emphasis on its scientific basis for non-specialists. Create Space. ISBN 1-4663-8460-3. William E. Hannam, Gerald E. Marsh, George S. Stanford. December 2005. Smarter Use of Nuclear Waste. Scientific American. The Restoration of the Earth. Theodore B. Taylor and Charles C. Humpstone. 166 pages. Harper and Row. 1973. ISBN 9780060142315. Sustainable Energy Without the Hot Air. David J. C. Mackay. 384 pages. UIT Cambridge. 2009. ISBN 9780954452933. 2081. A Hopeful Vision of the Human Future. Gerard K. O'Neill. 284 pages. Simon & Schuster. 1981. ISBN 9780671242572. The Second Nuclear Era. A New Start for Nuclear Power. Alvin M. Weinberg al. 460 pages. Prager Publishers. 1985. ISBN 9780275901837. The Nuclear Imperative. A Critical Look at the Approaching Energy Crisis. More Physics for Presidents. Jeff Eakins. 212 pages. Springer. 2010. ISBN 9789048186662. External links. The Integral Fast Reactor at Argonne National Laboratory. Archived material from a site about the IFR formerly hosted by UC Berkeley. Archived. Page index. Archived. Introduction. Archived. Integral Fast Reactor. Archived. IFR Metallic Fuel. Archived. Safety Characteristics. Archived. Fuel Cycle Facility. Archived. Fuel Manufacturing Facility. Archived. The IIFR Vision. Archived. Reactor burns waste as fuel in nuclear recycling experiment. Integral fast reactors. Source of safe, abundant, non-polluting power by George S. Stanford, Ph.D. Frontline interview with Dr. Till. IFR Q&A with Tom Blees and George Stanford. Integral Fast Reactors by Tom Blees. Part 2 of 3 interview with author Tom Blees about IFR. The IIFR's role in global warming.